This one says, find the amount of work in joules done on the surroundings when 3.98 liters of an ideal gas, initially at a pressure of 4 atmospheres, is allowed to expand at constant temperature to 14.57 liters by reducing the external pressure in 2 steps. First to 2.19 atmospheres, and I say this pretty explicitly, you will need to calculate the intermediate volume, that's going to be V2, using P1 V1 equals P2 V2. Then to 1.09 atmospheres, and your answer is the sum of the work for both pressure changes. And so the reason we want to do this, and I'm going to actually do this problem the way that it's asked for, and then I'm going in 2 steps, and then I'm going to do the problem in 1 step and show you that work is different depending upon the path. So this is a 2-step process. And we'll then do a 1-step process and show you that the amount of work you can get out of it, this process is different. And that's why work is not a state function. All right, so A. So we're first going to do it to 2.19 atmospheres. And let's see, so we have initial state. Because part of the work of this problem is just keeping track of all the pressures and volumes. 3.98 liters. So volume 1, P1 equals 4 atmospheres. And we're going to 2.19 atmospheres. And we don't know V2. But we do know the P1 V1 equals P2 V2. And we can solve for it. So I'm going to need to set it up. Four atmospheres, 3.98 liters. V2, I'm going to have to divide by 2.19. $7.27 liters. And that's less than my final liters. Shoo, good. Now for A, work equals negative of pressure times delta V. The pressure is always the pressure 2, or the last pressure. So this is going to be minus 2.19 atmospheres. And V2 minus V1. Uh, 3.98. There we go. And if I calculate this, I'm going to do my subtraction first. I get minus 7.21 liter atmospheres. Now for step B, I have a new system here, so it's going to be V1 equals 7.27 liters. V2 equals 14.57 liters. P1, which is again my new, so 2.19 atmospheres, and P2 is 1.09 atmospheres. So, and this is sort of the final stage for part 2, or part B. So I have work equals minus P times delta V. I always go with your second P. And then it's V2 minus V1. And I will multiply this out now. Do my difference first. I get 7.3. Oh, that should be liters. Sorry, 7.3 liters times 1.09 minus is minus 7.96 liter atmospheres. And so add up your two the amounts of work. Your work total is going to be these two added up, and they're both negative, so you're adding negative numbers. 7.96 negative minus 7.21. I get minus 15.2 liter atmospheres, which I then multiply times 101.325 to get minus 1540 joules. Any questions so far? Well, because what I'd like to do next is I'd like to now do this process in one step. So same process in one step, which means we go from V1 equals 3.98 liters, P1 equals 4 atmospheres, to V2 is 14.57 liters, and P2 is 1.09 atmospheres. And now work is going to be equal to minus P delta V minus 1.09 atmospheres. And then the difference between our final and our initial volume. Yep, everything now on screen. 14.57 minus 3.98 times 1.09 negative. I get minus 11.5 liter atmospheres. And we could turn this into joules, but I'm just going to stick with this. So here's the work that you can get out of a one-step process. And here's the work that you can get out of a two-step process. So minus 15.2 liter atmospheres. Work for a two-step process. And there's two conclusions that I want you to come to. Well, one conclusion you can come to from this, and it is a general conclusion. So conclusion, you can get more work out of smaller steps. I see a question. So the question says, where did I get the 14.57 liters? So the 14.57 liters was our final volume. And it was V2 at the end of our second step up here. So instead of going, so the two-step process went from 3.98 liters to 7.27 liters in one step. Cool. And then down to 14.57. And here we did it in one step. So, yeah, good question. Glad we got that. You can get more work out of smaller steps. And this is why so engines with smaller pistons are more fuel efficient. This is why engines with smaller pistons which generally means smaller engines, but this is why engines with smaller pistons are more fuel efficient. Which is pretty cool. So that's our one conclusion. The other conclusion is that the amount of work you get from a process is dependent upon the path that you take, and therefore work is not a state function. Any other questions about that? Okay.